let's look at a more complicated region that we need to integrate over and try to see if we can come up with the right way to address this in polar coordinates. So I have some function, z equals the square root of x squared plus y squared. And I want to find the volume of the solid that's bounded above by this, below by this, and also below by that. So I've got z equals 0, so that's the xy plane. So that's really, everything dashed here is gone. And then I've got x squared plus y squared equals 25. Well, x squared plus y squared equals 25 is just a circle of radius 5. But since there's no z component, it becomes an infinite cylinder with radius 5. An infinite circular, right circular cylinder. And then z equals x squared plus y squared is a right circular cone. And the reason why it's easier to think about it that way is, what if we converted that to a polar, or think like cylindrical coordinate equation, where x squared plus y squared equals r squared? Well, that tells me that z is actually equal to r. So that tells me that as r increases, z increases. So think of this being like sort of z equals r. It just goes along this line, but it doesn't matter what angle r is at, z has the same value. So z equals r is a cross section, but then you rotate it. And so if you think back to your applications of integration, you could take that and sort of slap it and spin it around the axis to get a volume of a solid of revolution. Same idea here. So anyway, what I've got is I've got something bounded below by 0. It's also bounded below by this circle of radius 5, and it comes up and it hits the circular cone at some point. But if you think about it, since z is equal to the square root of x squared plus y squared, well then when this is equal to 25, this will be equal to 5. So we're coming up to here to 5. And that's important because when we get our limits, that'll help us figure this thing out. So what I notice here is that my radius goes from, since I'm getting the region in between, my radius goes from 0 to 5. And since I'm rotating all the way around, theta goes to 2 pi. So that's actually fairly straightforward. And we already established that z equals, so our surface is actually just r. So the way that we would construct this to apply the integration would be the integral from 0 to 5, or rather 0 to 2 pi, 0 to 5, r dr d theta, which is really just r squared dr d theta, which then equals 0 to 2 pi, 1/3 r cubed from 0 to 5 d theta. Well, when r is 0, this whole thing's 0. When r is 5, that's 125 over 3 d theta, which is 125 over 3 theta from 0 to 2 pi, which is 250 pi over 3, which I would probably write it more like this, 2/3 125 pi. And you might ask yourself, well, why would I do that? Well, the reason is we want to use a little bit of intuition to make sure that we're not doing something dumb. So if I was to get the whole volume of the cylinder up to this point, the volume of a cylinder is pi, or a right circular cylinder is pi r squared h. And in this case, r is 5, but the height is also 5. So this is really pi r cubed, so that's 125 pi. And that's the volume of the cylinder. Well, the volume of a cone is 1/3 pi r squared h. For a right circular cone. And we already know pi r squared h is 125, and this is 1/3 of that. So if I subtract this from here, I get 2/3 of that. So my intuition checks out. So I have a reasonable belief that I've done this thing correctly.